I started at Case.
This meeting is being recorded.
And then I started at Case Western in 2012, where I've been, fortunate to be able to be a part of what I think is really amazing work with huge potential. So I just want to take the next hour or so to explain some of the work we're doing. As always, there's always a pitch. We are recruiting for a number of our studies. And so I just want to we're just hoping to get the word out there, show you some of what we've been able to accomplish, show you or help you meet some of the people who've been part of our studies, and hopefully even they can explain even better some of the work that we're doing. So with that, I will start by sharing my screen and share screen, and let's do. So can you all see my screen and see my slides? Yes, okay, wonderful. So as I mentioned, I'm part of Case Western Reserve University in the Department of Biomedical Engineering, also the Lewis Stokes Cleveland VA Medical Center. The Functional Electrical Stimulation Center has been around, probably by the time I was born, 40 years ago, it was 40 plus years ago. And they've been working to develop technology to restore lost function after spinal cord injury. There's a long history of what I would call clinical translation. So going from what we know, what we learn in the lab, to clinical trials and things of that nature. And again, I've been fortunate to piggyback off of a lot of the work that's been done in the past. The work that I do, or the focus of the work that I do, is to, in an ideal world, try to develop a system for people with chronic tetraplegia to restore the ability to perform meaningful, functional activities of daily living by direct thought alone. We are trying to develop two technologies, one known as a brain-computer interface, which allows us to record the movement intent, and then to use that movement intent to command a functional electrical stimulation system, which reanimates the paralyzed limb. So what I want to go through today is just kind of go through each one of these components, talk about their history a little bit, what we've been able to accomplish, and what we're trying to do present day. Okay. So as I mentioned, I'm part of the FES Center, which consists of clinicians, engineers, scientists from Case Western Reserve University, the VA Medical Center, University Hospitals, Cleveland Medical Center, and the Cleveland Clinic, all trying to develop technology to address different neurological injuries or neurological disorders, or ranging from stroke, spinal cord injury, epilepsy, for movement restoration, for pain mitigation, for different things such as bladder, bowel, sexual function, and a number of other applications. As I mentioned, the FES Center has been around for a number of years. Metro Health Medical Center is also a strong partner in this work. And again, FES as a technology, if you will, has been around and proven at least functionally beneficial, if not yet completely translated to be widely available, but at least has the promise we've seen of addressing a number of concerns which happen after spinal cord injury, stroke, and other. So as I mentioned, FES, we say what it does is that it speaks the language of the nervous system. As an engineer, my goal is to understand the central nervous system, understand neurological injury, and then figure out systems to help mitigate some of the resultant loss, including motor loss, sensory loss, and things of that nature. So that's where I'm coming from in terms of the goals of my work. Now, FES, as I said, we say that it speaks the language of the nervous system. We need to understand the code of the nervous system so that we can design different technologies to interface with the nervous system. A number of you are probably familiar with FES surface systems. So we can apply electrical stimulation using electrodes or contacts that are on the surface. They go through the skin to cause underlying muscles to contract. But a number of the systems that are developed at FES Center are actually using implanted devices. So there could be implanted electrodes around a nerve, which when stimulated, cause the muscles that are served by that nerve also to contract. We can also use electrodes which allow us to record from the brain, and that's part of the work that I do, so that we can understand for somebody who has chronic paralysis, what their intended movement is, and hopefully we can help recreate that movement using some of the electrical stimulation. So again, we're trying to marry two technologies, one known as a brain-computer interface, the other known as functional electrical stimulation. So what I'm showing here is just a schematic of an FES system probably around the late 2000s, 2008, 2010. And this individual has a high cervical C1 spinal cord injury, which caused loss of complete arm function on her right side and partial loss on her left side. She has this implanted functional electrical stimulation system, which when this clinician presses a button on this external stimulator, gives her the ability to hold an object between her thumb and her index finger, and it'll play again, which causes flexion of the elbow, so she can bring her hand to her face, to her mouth. And as you'll see in the video, allows her to flex and extend her wrist. And again, this is because there are electrodes which are implanted inside the paralyzed muscle, and when you apply a little bit, just a tiny bit of electrical current, you cause the muscles to contract, and you see the requisite movement. Now, systems like this have proven efficacious in terms of demonstrating that the technology is feasible. They haven't yet translated, as I said, to being ubiquitous, to being freely available. And there's been limited translation, admittedly, into people using them in their own home. But that's part of the work that we are trying to address with this particular study that I'm describing today and other studies as well. One of the challenges with many of these systems is that even if they could restore a number of different functions, there's always a question of how would somebody actually control it on a day-to-day basis? You can't have a clinician with you 24/7 necessarily pressing buttons on a box to initiate the stimulation. What my work does is it focuses on how do we give people who've lost a lot of function and have chronic and severe tetraplegia the ability to control a system which could restore arm movements and hand movements. Clearly, with a higher level of injury, there are fewer functions which are under voluntary control. And that's what this figure is showing here, that clearly the higher level injury, you have fewer and fewer control over, you have less and less control over, you have fewer and fewer voluntary muscles under control. So what we've intended to do is we asked, okay, what other sources of control could there be, particularly for people who have limited options? And so we have this working hypothesis that if we could actually record directly from the brain what the intended movement is, if we can decipher or decode that brain activity into an intended movement, we could potentially open up a new world in terms of what's possible for people with severe chronic tetraplegia to be able to control these functional electrical stimulation systems. And so what my work does is it asks the question, can we actually implant a small array inside the brain, record brain signals and relate them to the intended movements, and then give back to a person who has chronic tetraplegia, chronic paralysis, particularly upper extremity, the ability to just think about a movement, then have the electrical stimulation system reanimate the limb in that intended way. So that's the overall goal of the work that I've been doing for the past 10 to 15 years. Okay, so this has been, the work that I'm doing is also part of 2 clinical trials. So I just want to describe them very, very briefly, and then we'll get into the nuts and bolts of what we're doing. So when I first joined this group of collaborators, we were working on a clinical trial called BrainGate. And it's an FDA-approved trial which looks at assessing both the safety but also the efficacy of this brain electrode. This electrode which is implanted inside the brain, which allows us to record activity from the brain at a very high resolution. And what we've shown over the past 10 years is that we could use this brain electrode, which I will show in greater detail later, to give people who have chronic paralysis the ability to perform typing on a computer screen just by thinking about moving a mouse. As I mentioned before, our work is focused on giving people with chronic paralysis the ability to use their own thoughts to control movements of their own limb, which is functional electrical stimulation. So about 2014, so one thing I should say real quickly. So I should say that we are not the first group to investigate this idea of using a brain electrode to restore movement to people with chronic paralysis due to spinal cord injury or high stem brain stroke. There have been a number of groups since the mid-2000s who have investigated this technology in humans, in people, to show that it's relatively safe, to show that the surgery has minimal complications, and to show that the technology, the brain recording technology, could be effective for giving people with chronic paralysis, in this case, the ability to control, for example, a robotic arm, to perform reaching, grasping of objects just by their own thoughts. What we want to do is not have people control robotic arms, but we want to restore the ability to control their own limbs through functional electrical stimulation. This video, actually, in the bottom right, shows an individual who was at Ohio State University using this brain recording technology. As you'll see, he has some residual arm movements. He has compromised grasping movements. He can't really grasp the object by himself, but using the brain electrode and a surface FES system. These are surface electrodes which stimulate the underlying muscles. It can give him enhanced grasping capability. But again, the work that I'm doing is focused on people with high cervical spine to restore the ability not just to grasp objects, but also to reach to those objects. So in about 2014, we recruited our first participant into this BrainGate clinical trial in Cleveland. Prior to that, I was working with a participant in Boston. But this participant was our first participant in Cleveland in 2014. He actually received, and I apologize, I should have given advance warning about the graphic nature of this slide, but he actually received 2 brain implants inside a part of the brain known as his motor cortex, his primary motor cortex. It's a part of the brain which, if we can record those brain signals, it's directly related to intended movements of the hand, intended movements of the shoulder, intended movements of the elbow. And so what our working hypothesis was essentially was that if we could record those brain signals, then we could also give him electrodes in his arm and in his upper arm and lower arm. Then by recording those brain signals, if we could figure out what the patterns of brain activity mean using statistics and other algorithms, we could then essentially circumvent or go around his spinal cord injury and reconnect the movements of his arm and his hand back to his brain. So again, he could think about moving and his arm and hand would respond, hopefully in the way that he intended, assuming our algorithms could decipher those signals. And that's what my laboratory deciphering the brain signals. So, we coded him as participant T8, but he was actually a cervical level 4 spinal cord injury with ASA A designation. He had been injured 8 years prior to joining our study. As I mentioned, he received these microelectrode arrays inside his brain. He also received electrodes inside his muscles for reanimating his limb. One of the challenges we had to deal with, because he had been paralyzed for many years prior to joining our study, is muscle fatigue. If the muscle would fatigue quickly during electrical stimulation. So we actually helped him exercise his muscles, when he wasn't working with us, just using cyclical electrical stimulation to build them back up, to build their resistance to fatigue, to rebuild their strength. And we found that it was quite effective and allowed him to really participate in our study. Using these electrodes, we were actually able to restore to him the ability to flex and extend his wrists, the ability to open and close his hand, the ability to flex and extend his elbow, and the ability to move his shoulder up and down using an assistive device known as a mobile arm support. Okay, so what I want to show you next are a series of videos of him actually using our system, and then I'll actually let him tell you a little bit about his story and why he joined our study. I see some chats. Oh, all right, am I audible? Can everybody hear me, hopefully? Yes, okay, thank you. Okay, so I also want to make sure that the sound, yes, I'll share my sound. So what you're going to see next is a video of our very first participant training to use our system. What you'll see is that he will have 2 connectors connected to the pedestal. Oh, actually, let me show you one more slide, and then I'll show you that video. So this is an image of what the brain connectors look like. So it is what we call percutaneous, meaning that it does protrude through the skin. When it's not in use, it is actually covered by a cap. And we are very meticulous in terms of guarding against infection, cleaning, making sure it's cleaned reliably. And again, this participant had this device for I believe 6 years without any complications. We have another participant enrolled right now who also has this device. In the past 20 years, I'd say about 12 to 15 people in the world have had this device with minimal complications as well. It is still a research study, so I will say that, but it does have a long track record of safety and efficacy. So the pedestal is external. When we want to use the system, there is a cable which is connected to the pedestal, which you'll see in the next video. And then this just shows an example of the wires that were implanted in our participant. They are also through the skin, and then we connect them to the stimulator to reanimate or cause those muscles to contract. Okay, so what you'll see now is our participant. This is Mr. Bill Kochevar. He was our first participant in our study. You can see the cables which are connected to the pedestal. So again, so just for transparency, it's not a fully implanted system. But those cables allow us to record his brain signals at a very, very high resolution. We're recording the brain signals, and then we're deciphering what movement he wants to do with his elbow, or what movement he wants to do with his hand. So what you'll see is sometimes his elbow will flex and extend as it's extending now, and then sometimes you'll see his hand open and close. So he's actually controlling movements of his own hand using the brain system and the FES system for the animation. The video will play again. What we're doing then also is we're actually measuring how much he's moving his elbow. We're measuring how much he's opening and closing his hand, and we're having him train in this virtual environment. So when he moves his hand and his arm, this opaque hand and arm also moves. So he's actually controlling this virtual hand and arm. And his goal is to essentially match the position of a translucent hand, which basically represents a target arm and hand position. And every time you hear that ding, it shows that he's actually hitting the target. So what that means is that he's able to precisely control movements of his hand. It'll play one more time. He's able to precisely control movements of his hand and arm to match target elbow position and hand position of this ghost, what we call this ghost hand, that we again just use to see how well he can control his basic. He did extremely well, and I'll even say he was actually able to do this on the first day. Now, he got better with more training, but by him being able to do this on the first day, that suggested to us that we were actually recording from the parts of his brain which were still intact and which still represented the movements that he. Okay, so I'll also, just real quickly, I also show one other video. In addition to hand movements and elbow movements, we also were interested in when we actually get information about if you wanted to make what we call dexterous finger movements. If you wanted to be able to control his thumb or his index finger, is that information also represented in his brain? And so we had him play a similar game and saw that, again, he could actually control movements of his fingers quite nicely just by thinking those thoughts, and then he could control movements of his virtual hand. And our goal is to then restore these actual movements with his own movement. Okay. So rather than me, just talking about what simple movements he could do, we wanted to ask the question: okay, what meaningful movements could he do? He said that he always envisioned being able to take a drink by himself and feed himself. And specifically, he loved mashed potatoes, so he really wanted to be able to eat a bowl of mashed potatoes. So we just wanted to see if he could learn to combine these relatively simple restored movements, being able to grasp an object between his thumb and index finger, being able to control movements of his elbow, and being able to control movements of his shoulder. Could he learn to combine them to produce a meaningful activity of daily living? And what we were very, very pleased to see is that, in fact, he was able to. And in fact, his own words, what he said was that he was often asked the question, what are you thinking when you are trying to get your arm to move through this brain electrode and this electrical stimulation device? And he said that he doesn't have to concentrate that hard. He literally just thinks about moving his arm and hand naturally in the way that he did before his accident, before his injury, and his arm responds in the way that he intended, the way that he intends. And that was music to our ears. Again, that told us that we were in the right part of the brain and that we were able to we were decoding or deciphering the brain patterns correctly, and that we were able to reanimate his arm and hand in the way that he intended. Okay. One more video, I think I will. So as I mentioned before, there was actually a movie made about Bill Kochevar. The movie is called I Am Human. And it talks about why he felt compelled to be a part of the Cleveland FES Center, why he felt compelled to be a part of our study. And I just have to say that I could not have envisioned a better person for us to start working with. First, he was extremely selfless individual. And very intellectually engaged, and was a part. He wasn't a research participant in so much as he was a part of our team. And so that movie called I Am Human does a great job talking a little bit more about the technology, but focuses also a lot about his life and why he wanted to be a part of our study. And so I just want to play just a short, about minute clip from that movie where you'll get to hear him talk about why he wanted to be a part of the study. If the sound does not come through, please flag me down, because that's I really want you to hear what he has to say. Oh, whoops, sorry, not working.
Well, it was amazing because I thought about moving my arm, and it did.
We've been able to take the electrical signals which represent his thoughts and use that to control stimulation of his arm and his hand.
We've bridged his spinal cord injury. He can now think about moving his arm, and his arm moves.
I get to be the first one in the world to do it.
He has a severe spinal cord injury. He is paralyzed from the top of his shoulders down.
They have to turn me every 2 hours. If I want water, they have to give me water. This research has enhanced my ability to be able to do things.
For the first time, we've implanted brain recording electrodes in a person, and an FES system, functional electrical stimulation, has been implanted as well.
We are just at the forefront of really understanding how the brain functions, how to take advantage of our knowledge, and could see exponential growth. So if you have 90 minutes, I definitely encourage you to consider looking for the movie I Am Human. It is on Amazon Prime, Hulu, and one other medium, I think perhaps Roku. But again, it explains the technology a little bit, but it also allows you to meet our very first participant, Bill Kochevar, and it really highlights the contributions he made towards advancing this technology to restore function of people with chronic. Okay. One of the major challenges with chronic spinal cord injury is that not only is there motor loss, but there's also oftentimes loss of touch, loss of what we call somatosensory functions, the ability to feel when you're touched or when something is touching. We know that this tactile feedback and this touch feedback is really critical for interactions in the world, interacting with objects, interacting with other people. So, with Mr. Kochevar, we were only focused on and only able to restore admittedly limited, but some functional amounts of movement. But sensory or sensory restoration is equally as important. So one of the questions that we're looking at now is how can we restore not just movements, but also touch sensation back to those who have lost it due to spinal. A number of my collaborators have investigated this similar question with a different population of people, most notably people who have lost their limb due to amputation. And what they've shown is that we can actually use electrical stimulation. This represents one of the electrodes around a nerve inside the arm. And by applying the right patterns of electrical stimulation, you can actually give somebody who's lost their arm and hand the ability to feel parts of their hand, even though it's no longer present. And this is because of the electrical stimulation technology. And so what we hope to do is we've asked the question, okay, so this technology applies to people who have lost their limbs due to amputation. Can we also use similar concepts to give lost touch sensation to somebody who has a high level cervical spinal cord injury? And so that's one of our goals, in addition to restoring movement. One of our new goals through the ReHAB clinical trial is to be able to restore not just movement to individuals with chronic, but also restore touch sensation. And I'll talk about some of the work we've been able to do. Okay, so I will say that again, that the ability to restore touch sensation, again, comes from these electrodes, which are implanted not in the motor part of the brain, but they are implanted in what we call the somatosensory, primary somatosensory cortex. By directly stimulating parts of the brain, you can actually give people a sense of touch, even if you're not actually touching. And so some of our colleagues and collaborators have shown that if you put these electrodes inside the brain, and you pass very, very tiny amounts of current through them, somebody who has arm and hand paralysis can report feelings of touch on different parts of the hand. Now, that's really encouraging because that suggests that not only can we use these these electrodes to record information from the brain that tells us something about movement. We can also use it to write information or stimulate the brain to give a sense of touch, which again, we believe is critically important to interacting with objects and interacting with other people. So within that context, we've established what is called the ReHAB clinical trial, which stands for reconnecting the hand and arm to the brain. And in this clinical trial, our goal is to restore both movement and sensation to people with chronic high cervical injury. Our goal on the movement side is to restore what we call complete arm function. So this includes movements of the shoulder, movements of the elbow, movements of the hand, including just whole hand grasping, but also individuated finger movements, dexterous finger movements, because we are using a newer form of the FES technology, which could give us access to the nerves and muscles which are underlying those more complex movements. So again, this is under FDA approval. So we have the proper regulatory approval to pursue this. We've currently recruited, enrolled, and implanted one participant into the study. And so I want to walk with you through a little bit about what the participant underwent in terms of the surgery and some of the initial function that he's been able to restore, to see restored. So let me this. So I'll just show you. So this participant actually underwent 2 surgeries. So the first surgery was to implant the electrodes around his nerves. And again, I apologize for not being fair warning about the participant, who we refer to as RP1 in code, essentially went through and received electrodes around different nerves of his upper arm. And by activating these nerves, it allows us to restore many different functions of the arm, including shoulder movements, shoulder flexion extension, movements of the forearm, including extending and flexing your elbow, pronation, supination, so the ability to rotate your wrist, the ability to flex and extend your wrist, and movements of the fingers, including that of the thumb as well. So because we're using this new FES technology, we're able to at least actuate, in theory, more capabilities, more functions. In addition, he also received electrodes in many different parts of the brain. Some of the electrodes allow us to record brain signals related to movement. Other electrodes, like these 2 labeled S1, allow us to stimulate his brain so that he feels, so that he reports a sense of somebody touching his hand. So what I want to show you here is so this is our participant. He's known as RP1. And actually, I can tell you his name. His name is Austin. He was actually featured in a PBS special, which I'll show you just a short clip of in a little bit. But I just want to show you just a little bit of what's involved, of what Austin is involved with. So as I mentioned, he sustained high cervical injury probably about 6 years ago prior to joining our study. He has no movement below the shoulder of his own volition. He does have some limited intact sensation, but not enough, but where our goal was to enhance it. So what you'll see here is him using the system to control movements. I believe this video is to show movements of his elbow. So I'll just play it and then I'll show you a few more.
Reflection.
So this is Austin controlling his ability to flex his elbow, and then relax. He's wearing this glove, and I'll talk about this glove later. It just allows us to measure the movements. But in this case, the FES, electrical stimulation, is causing just a simple demonstration movement of him flexing his elbow. In this video, he is actually this one. In this video, he is similar to what you saw Mr. Bill Kochevar doing previously. Austin is controlling opening and closing movements of his hand. They are measured by this glove and recreated in this game. And again, we're just trying to assess how well he can, of his own volition, open and close his hand. Again, just by thinking about it and having the FES system animate his and the way that he is intended. So Austin is actually at, he lives a few hours away, but when we run these sessions, he comes to us at the Metro Health Medical Center, and we're able to work with him in about 2-week blocks and make our system better understand how his brain is working so that we can develop better algorithms to help give him, better function, okay? 2 more quick videos, and then I think, for the sake of time, we'll be over. So this video shows what you're going to see is Austin. Hopefully the sound will come through. You'll hear him articulate what he's thinking about as he's making these movements. And he'll be able to tell you that he's getting ready to open his hand and getting ready to close his hand. So you'll see that it is actually, in fact, under his own volitional control. He actually has a more advanced brain system than what Mr. Bill Kochevar had. So remember I said that you saw with Kochevar, he had the larger cables which were connected to his pedestals. So Austin actually has a much smaller footprint, a much smaller profile. But again, it is still percutaneous. We still do have to connect him up and disconnect him for the purposes of the study. But when he's not in the study, he is not at all in any way, shape, or form connected to any of our systems. So let me play this video, and then you'll get to see a little bit of his hand.
Recording.
Thinking about closing.
So he just said he's thinking about closing.
I'm constantly thinking close. Sure will sound very pleased it's doing. Trying to always get it close to me.
He's still thinking about closing. In a minute, he'll start thinking about opening.
We switch. It's just harder, I guess, John, but people get it.
So it takes him a little while to get used to this system.
So you feel like you're able to get it to extension, but then it kind of goes, like slows on its own?
Yeah, more so, like, I'm not getting that, because I can tell at times I'm doing the right thing, because I can feel the nerve. I always get sensation with extension before I feel the movement. And so like right there I got it. Then I don't know why I went to close. Like I can feel me on it, but it's not pulling them out. I'm not getting to 100% from back to close. That's open. So I feel like I can switch in a heartbeat to close. Close. Close.
So he said he feels like he can switch in a heartbeat between opening and closing.
And each of those poses is volitional? It's not.
Yeah, I would say So that one I wasn't really thinking. Calm down more. Now I'll go. Overpower. Close. Open. Close. Open. Close. Open. Close. Close again. See, I'm on open, but there it goes finally. Open. Try and do 2 opens in a row. Close. Try to do like 2 closes in a row.
So is that his voice? So yes, so that is Austin. He's our current participant, where he was, and I apologize if you couldn't hear very well, but what he was articulating was, he was saying that I'm getting ready to do 2 closes in a row, 2 opens in a row. And so he was voicing his intention before he did the actual movement, so that we would know that it was actually him performing the movements of his own volition. So this just shows a very simple snippet of again, just a very basic hand opening, closing pattern. We also have patterns for, and he's shown his ability to move his elbow of his own volition. And what we're working on with him is similar to Mr. Kochevar previously, that he will learn to combine these simple movements into a meaningful functional activity, such as feeding himself. Austin said that prior to his injury, he loved to paint. One of my personal goals is to have him be able to hold a paintbrush and make strokes which are meaningful to him. And that's really our goal in this study. It's not just necessarily to study the brain or to do, a fancy science project, if you will, but really is to say what is possible in terms of restoring function and restoring control back to somebody like Austin, who is cognitively engaged, cognitively advanced, still wants to be, active. He's young and ready to go, and to say, in what ways can you enhance independence to a degree, and quality of life. So,
Recording.
So one more video, and then I think we'll be done here. So as I mentioned, there was a PBS special that Austin was a part of, and I just want to show that real quick. It's about 6 minutes long. Okay, so I just want to show this video of PBS came and did a quick special on Austin. I just want to play it. I think we're close to running out of time, so I definitely want to leave time for questions. So I might stop it early, but again, just so that you could hear from him, his story, why he chose to be a part of our study, and what he's hoping to get out. So I'll play this. Hopefully, again, the sound will come.
Next, we look at the forefront of research to improve the lives of people living with paralysis. Finding a way to bridge the severed connections between their brains and their limbs remains an urgent but often elusive goal for researchers. As Miles O'Brien reports, they are making steady progress, and they have a good feeling about restoring some people's sense of touch. This is the latest in our Breakthroughs series on invention and innovation.
Austin Beggin was 22 when his life changed in an instant. A dive into some shallow water left him with a broken neck between the C3 and C4 vertebrae.
At that level, you're talking about breathing, you're talking about swallowing, you're talking about pretty much everything that comes with it as far as how severe of an injury it is.
When he first started living with quadriplegia, he imagined himself getting better.
Hey, Austin. How you doing, man?
Good, Bob, how are you?
Yeah, great. Come on in.
You're always thinking you're going to wake up the next day and it's just going to come back. 3 months with really no motor gains kind of set in like, okay, this might be more of a long haul.
Now 6 years since his injury, He is a volunteer participant in a groundbreaking project aimed at changing the long haul for people with paralysis. The big goal is to find a way for them to move their hands and regain sensations of touch. Austin Begin is just getting started moving his hand for the first time since his injury.
It really is remarkable that these little wires coming out of my arm, you know, are allowing something like this to happen.
What does that feel like?
Just the fact of feeling the arm move is the remarkable part of it. I mean, I could do this all day, just have it go up and down, up and down.
It's a project run by Cleveland's pioneering Functional Electrical Stimulation Center, part of the Lewis Stokes VA Medical Center. For 30 years, they have been innovating technology that restores function for people with paralysis.
We are presently trying to understand the underlying mechanisms of the brain that relate to movement and also sensation. Also, I'm just looking through your spike panel right now, and it seems like we have a good number of action potentials, so your brain is working.
Biomedical engineer Bolu Ajiboye is the principal investigator.
We would like to be able to design technology that records from the brain, bypasses the spinal cord injury, and allows the person to control meaningful movements of their hands, such as positioning their arm in space, moving individual fingers, being able to grasp different objects so that they can perform many activities of daily living that people take for granted every day.
It begins with brain surgery. Austin Begin's operation was done by neurosurgeon Jonathan Miller with University Hospitals Cleveland.
So this is the electrode we implant into the brain. As you can see, this is the part that goes in. It's very small. Actually, there's a total of 6 of these that we implant for this particular project, going into 6 different areas of the brain.
But where in the brain? Simply targeting the area that controls the nerves that fire muscles is not enough.
We're interested in the areas of the brain that are responsible for motor planning, for not just the actual individual nerves that control the muscles, but also the neurons that are upstream of those that control what it is that the person wants to do.
In another operation, surgeons implanted electrodes to stimulate Begin's hand and arm muscles. The surgeries were just the start of a long journey. The team is now busy trying to decipher the myriad of signals from Begin's brain measured in microvolts.
What we're interested in is the fact that we're not just looking at one cell, we're looking at hundreds of cells. And there's something...
This is where you get the pattern.
This is where you get the pattern.
But so if he tried right now to move his finger, some of these panels would light up more than others.
The firing rates would change.
I see.
Right. And that change can, to the naked eye, maybe be a little bit challenging to detect. But our algorithms can detect the change, not just, again, in one neuron, but across the population of neurons.
The algorithms are programs that can identify subtle patterns of brain activity across many neurons linked to specific movements. To improve their accuracy, the team has Begin play games. He imagines moving his paralyzed arm to match what the animated hand is doing on the screen.
There is learning on both sides, actually. So our algorithms get better and better with more information that we have from the participant. At the same time, there is an opportunity for learning on his end as well.
What they're doing here is unique, but there are several other projects underway aiming to understand the activity of the brain during various functions. Some use brain signals to control robotic arms or enable communication. Austin Begin's predecessor in this project was Bill Kochevar. In 2014, he became the first person in the world to be able to use this system to control his own limb. He was able to open and close his hand, move his wrist, elbow, and shoulder, but he had no sensory feedback. Giving paralyzed people a sense of touch is biomedical engineer Emily Grotchik's priority.
Very little is known about the neural language of touch in the human brain, and that's something that we hope to study here in this project.
Eventually, they will give Austin Begin a glove with sensors in the fingertips. The hope is they will send sensory information to his brain implants.
Without sensory feedback, you really don't know how to control the motions that you're producing. You don't know how to control the forces you're exerting on an object or the positioning of your body.
But there is more to touch and motion than that. Something harder to quantify. Something Austin Begin understands profoundly.
People say, like, what would you love to do? I mean, if I could actively shake someone's hand, I mean, what would be, you couldn't put a price on that to me.
A lot of the technology this team is refining to help paralyzed individuals came out of a lab nearby, one focused on a disability that is part of my reality. In my next story, I'll show you how amputees are learning to feel things through their prosthetic limbs. For the PBS NewsHour, I'm Miles O'Brien.
Such fascinating research. We'll have that follow-up report from Miles next Wednesday.
Excellent. So, so I hope that little snippet gave you just a sense of some of the work that we are presently doing. We do have a number of exclusion criteria that I won't belabor all the different points to you, but we are presently recruiting for the study that Austin Beggins is a part of. So our hope is that, we're able to reach out to different groups. And if you know of anybody or yourself are interested in potentially being a part of such a study, we would love to be in contact. There are some limitations in terms of geography. We typically recruit within a 3-hour drive of Cleveland proper. And there are a number of other indications that we're looking for in terms of limits to age, limits to, previous medical history. But, if at all interested, I can leave these inclusion-exclusion criteria with you all. We're actually on the clinicaltrials.gov website. We are also listed on scitrials.org. And I would encourage you to look for our ReHAB clinical trial. And again, if you are interested or know of anybody who might be interested, we would love to be in contact with them or with you. I can also leave my contact information and that of Dr. Miller, who is a surgeon who performs these surgeries. And we also do have a website, rehabstudy.org, that explains again what the purpose of our work is, who we're recruiting, and additional information. So there are a number of people who work on this, graduate students, collaborating scientists, co-investigators, doctors, nurses, et cetera. It takes a big team who have many years of expertise in history in terms of working in this space. And so again, we would love to have new participants join our team. We are always very much indebted to the contributions of time and personal contributions that individuals make to our team's research. So with that, I'll end. This work is across many different institutions across the country, many different institutions in Cleveland. We're funded by a number of federal agencies who are interested in this research for, restoring function to veterans and others with chronic spinal cord injury. I should mention actually Mr. Bill Kochevar, who was our first participant. He was a Navy veteran. And so he was actually housed at the VA, and we were able to work with him at the VA. As I also mentioned, there is a movie, I Am Human, which again describes not just the science and technology side, but also the human story of Mr. Bill Kochevar and why he wanted to be a part of this work and what contributions he felt. So if you have 90 minutes or so, I encourage you to watch the movie. It's very well done, in my opinion. And with that, I will end, and I can take any questions that you all may have. And again, I really do thank you for the opportunity to speak.
Great, thank you. Are there any questions?
So there's one question in the chat that says that what about for people with lower extremity paralysis? Are there studies available? And the answer is yes. So my expertise and my research is in restoring upper limb movement. However, the Functional Electrical Stimulation Center, and there's another center called the APT, or Advanced Platform Technology Center, They do work on restorative technologies for lower extremity function, including standing, including postural support during wheelchair mobility, including standing, stepping, transfer. And so that work is another big push, another big focus of the VA. You do not have to be a veteran, of course, to be a part of these studies. The work is funded by the VA because the VA has a special interest for veterans, but anybody who is interested in becoming a member of this, becoming a part or contributor to these studies, very much can do so. There's a website which just want to make sure I get the website correct. I think it's fescenter.org. Let me verify the website before sending you down the wrong place on the internet. So if you can try that website. So I'm having internet problems. Make sure this is the right website. So yes, if you go to fescenter.org, it actually, and I'll share my screen one more time so you can actually see where you will end up. Okay, so if you go to fescenter.org, what you will see is a description of our Cleveland FES Center. We have, if you go under research participants, you can read some of the previous participation, some of the testimonials. If you go under research, it actually shows you some of the clinical trials that we're currently undergoing. And so reaching and grasp is what I work on, but other investigators work on restoration of cough, restoration of pelvic function. Stroke is another application. There's pain, TBI. And we also do have lower extremity applications as well. So I encourage you to peruse this website. If you're all, again, interested in joining any of the studies, there's contact information and somebody can for sure get in touch with you to at least explore those options.
And
there's a question from Julie: would this work for someone with paralysis from a brain aneurysm? Also, any chance this research was started by Dr. Petrovsky in the late 70s and early 80s? So I don't know that I'm not familiar with Dr. Petrovsky. I know that this center in particular was started in the mid to late 80s by Dr. Hunter Peckham, who was a professor emeritus at Case Western Reserve University. He is now at Metro Health Medical Center and the Cleveland VA as well. But he built off a strong foundation from other investigators who came before him. Dr. Petrovsky's name I'm not as familiar with, but it may be possible. The question of would this technology work for somebody with a brain aneurysm? So remember, there are two technologies. So there's the brain recording technology, and there's the FES, or electrical stimulation technology. The electrical stimulation technology for reanimating the limbs works if the nerves that serve those muscles are still functioning. So long as those nerves are functioning, then absolutely FES can be applicable. On the brain side, so long as the brain networks are still functioning, we can record from them and decipher their intent, then it is possible to use this technology. So somebody who's had a stroke, brain machine interfaces could potentially be of benefit, but we'd have to think about it on an individual basis.
I did want to add that the SCItrials.org website, so SCItrials.org, you can create a profile, put in your injury level, I believe your complete, if you're complete or incomplete, your location, what research you're looking for, and the SCItrials.org website pulls all of the research clinical trials from clinicaltrials.gov that are recruiting spinal cord injury and like filters it into one place. The website was built with voices from spinal cord injury survivors, people living with spinal cord injury. It's very user-friendly. It's a great resource if you're looking for research, clinical trials. Any other questions? Okay.
If there are no other questions, I sincerely thank you all for the time.